All right, so I wanted to do a quick video just talking through some of these examples from the notebook to help contextualize them. I will put these on the Google Classroom as well, so you don't have to pause the video right now and copy, just sit and watch, and then there'll be a copy on Google Classroom that you can copy as well. So we got a what we'd call a physical pendulum, which is where mass is not just concentrated at the end, and gravity pulls on the center of mass of both of these. And as the pendulum swings, the angle that gravity makes with the r vector, which would go from the point of rotation to the spot where gravity is applied. So the angle between the rod and vertical changes. That means that torque is not constant, and we couldn't use kinematics. Basically, solving the sigma tau equals I alpha equation becomes very difficult. So we're going to use energy here. Another clue that it's going to be good to use energy is that we're looking just for speed of a block at a certain point. So we can use the difference in height to help us find speed when using forces, or torques in this case, isn't as convenient. So we got our initial energy plus the work external or non-conservative, which there is none, we're ignoring drag, equals energy final. At the end, all of the final energy is purely rotational because the center of mass of the rod and the center of mass of the block are as low as they're going to be. Initially, they both have some potential energy, and I've kind of defined the zero level to be, so this is zero for the mass, and then for the rod, I would kind of take like that level there, y equals 0 for the rod. So we look at like the change in height of each of them. And we've been through this before. You can set up a triangular relationship here. That's height, that height h. This is going to be L minus h because that whole thing is L. And then use a trig relationship here. You use cosine. And the center of mass of the rod, which is halfway up, drops half the distance as the bottom does. So we have two types of gravitational potential. This is for the mass at the end of the rod, and this is for the rod itself. All of that gravitational potential gets converted into rotational energy. The rod is rotating about this point, which is fixed. It's not moving, so all of the energy is rotational, not translational, because the point of rotation is not moving. So I solved this out for omega, which I found is a decimal, and then I went back and did r omega to find the velocity at the very end. I could have waited, or I could have done this earlier. It's just a matter of preference. So there's that. In the next problem, same kind of thing, but we don't have a mass on the end this time. Here we're looking for angular accelerations at various points or at a specific angle. So we're not looking to find the angular acceleration as a function of time, just what is it at this specific time. Because we're not looking to find it as a function of time, or we don't need to find acceleration, which we would then use to get speed, it makes this one a little bit easier. So the sum of the torques about the end, where it's attached to the wall, is I alpha. I is 1/3 ml squared, the moment for a rod about its end point. So I solved that out for alpha, and at the beginning, at the very beginning, gravity is 90 degrees. So at 90 degrees, alpha is 3g over 2L. And for part B, it says the initial downward acceleration. So we're looking to find the downward acceleration at a point that's 0.25 of the way along. And I'll actually take this, which was in blue. And I'm going to change that just to stick out a little bit. I'll put that in orange. And then I'll make an orange dot here at 0.25 of the way. So we're looking to figure out what's the initial downward acceleration of that point. And alpha is, oops, A is going to be R alpha. So we just take our value for R and multiply it by the answer that we previously got here for alpha. Do that for all 4 points. Halfway down the rod, we were right there. That's at the center of mass. 3/4 of the way down the rod, we would be right there. And then all the way down at the end of the rod, we're over here. Now, as this swings down, some of those dots are going to need to move faster than other ones. So we shouldn't be surprised that they have different accelerations, because to cover the same amount of angular change in the same time, it's going to take them the same time to do half a rotation or to do a quarter rotation to where they're hanging straight down. So if it takes the same amount of time for this red dot to get down to here as it does for this orange dot to get down here, look how much farther the red dot has to go. So it's got to have a greater acceleration to cover the same distance, or to cover a greater distance in the same time. So at 0.25 L, it's 3/8 g. That's less than half the normal acceleration due to gravity. At halfway out the rod, we're accelerating at 3/4 of the gravitational acceleration as if it was in free fall. The green dot, interestingly enough, actually accelerates faster than gravity. And the red dot even faster yet. The red dot accelerates at 15 meters per second squared. That's 3g/2. So these last two dots here are actually accelerating faster than if you had just dropped the rod and it wasn't attached to the wall at all. Pulley example. I've drawn the forces on each of the objects in different colors. For the pulley, we're concerned about torque, so I drew the forces where they act. I'm not concerned about the forces here at the center, which would be the force of gravity down, and there'd be a pivot point. Excuse me, there'd be a pivot point up, but those two forces cancel and they don't provide any torque. Our coordinate system, we're going to go down on the right because it tells us capital M is bigger than little m. I labeled these 1 and 2. So I chose down on the right to be positive. Notice that that means a clockwise rotation is positive and a counterclockwise rotation is negative. This is a little different than our standard system. So you apply Newton's laws for M1, M2, and you apply the rotational equivalent of Newton's laws for the pulley. For the pulley, alpha is going to be A/R, and that will help because that R on the bottom cancels with one of those on the top, leaving us a single R on the right, which then cancels off with the R's on the left that were part of the torque formula. We get these three equations, and then we're going to add them together. Notice that all the T's cancel out, and then we can pretty easily solve for our acceleration. Another way of doing this same problem would be with energy methods. This mass drops a distance of h, this mass rises a distance of h, and the mass of the pulley does not change height. So at the beginning, we have the potential energy of these two blocks. I didn't include this pulley because the potential energy of the pulley at the beginning would be the same as the pulley at the end. So I just didn't even include that. At the end, this mass is down at y=0, and this mass is up at 2h. So you got to make sure you include that final term there. And then both masses are moving with a velocity of v, and the pulley is rotating with energy 1/2 I omega squared, and omega is v over r. So we plug in everything here, all those r's and stuff cancel out. We can factor out a v squared over 2 from everything here. And this term, I moved it back over to the left. So m1gh minus 2 m1gh, that's where this minus m1gh comes from. I can solve this out for v squared, which is the velocity after falling a distance of h. And since our acceleration is constant here, I can use kinematics to come up with an expression for the acceleration, which was the ultimate goal of this problem. When I plug everything into that equation, I get this, which if we go back and look at the previous question, this and this, it should be the same acceleration since we're dealing with the same problem. You are then going to take, and for example 2 here, you're going to do all the same kind of stuff that I did up here. I want your work to be equally as organized as mine. Color-coded if you want. Equally as organized. I want to see the forces drawn out and labeled. I want to see some of the heights and stuff marked. I want to see coordinate systems labeled. I want to see formulas written out, things plugged in, crossed off. Nice, organized work. Both of these problems should end up with an acceleration of this nature. The mu in here comes with friction. And there you go. Get that stuff copied and done. 43, 42, and 41. Get that done for class on Tuesday. Have a good one.